thanks for clicking. Welcome to another Narculus production. Today we're going to be talking about separable differential equations with particular solutions. Okay, so in the last video we talked about general solutions. We left the plus c in it. Now we're going to talk about a solution where you'll be able to find and calculate c so that there won't be c in there anymore. It'll be replaced by an actual constant or an actual numeric value. All right, so let's get started. Most of this stuff you already know. Okay, we've already done it. So our technique to solving a differential equation here is separation of variables. Still the same steps at the beginning here. Okay, gather your y's and dy's on the left, x's and dx's on the right. Normally, integrate both sides, add the constant of integration to the independent variable side. Step 4, there it is in the middle. So in step 4, you're going to use the initial condition to solve for c. Okay, stick it back in there, put that number in there, and then you're going to go solve the equation for y. So we threw one step in the middle here. All right, that kind of adds to the work, one extra step. Okay, all right, so let's get started. Let's see how it all works. Okay, I want to find the particular solution y equals f of x to this differential equation with initial condition f of 4 equals -3. All right, so first thing I'm going to do is I'm going to separate my variables. So I'm going to multiply both sides by y, multiply by dx as well. So I'll have y dy equals 3x squared dx. And now I'm going to integrate on both sides. The integral of y dy is y squared over 2. The integral of 3x squared is 3x cubed over 3 plus c. So y squared over 2 equals x cubed plus c. All right, now, normally we would take this and solve it for y, but instead of solving it for y right now, we're going to take this initial condition, x equals 4, y equals -3, and we're going to plug it in to find c. So we have -3 squared plus, or over 2, equals 4 cubed plus c. So 9 over 2 equals 64. So 64 minus 4.5, right? 4.5 would be 59.5. Oh, negative because I got to move it over here. So -59.5 is equal to c. Yeah, I think that's right. That looks good. Okay. All right. So now we have our equation is y squared over 2 equals x cubed minus 59.5. Okay, so far so good. But I want the particular solution y equals f of x. This has to be solved for y. So now I got to solve this thing for y. So I got to keep going. Multiply both sides by 2. So we got y squared equals 2 times x cubed minus 59.5. Okay. Now I got to get rid of the square on both sides to get y alone. Take the square root on both sides. I need a plus or minus because it took the square root. So y is equal to plus or minus the square root of 2 times x cubed minus 59.5. But here's the problem with y equaling plus or minus the square root of 2 times the quantity x cubed minus 59.5. This is not a function. And I'm going to come over here and show you why real quick, because it could be plus or minus. So which half is it? The top half or the bottom half? Okay, this is a little bit more familiar to you when you looked at circles. So we've seen this before in the class. Let's say I had a circle with the equation x squared plus y squared equals 1. If I solve for y, I get y equals plus or minus square root of 1 minus x squared. So x squared plus y squared equals 1 is a circle with radius 1. So when you solve it for y, you're getting plus or minus square root of 1 minus x squared. What that is referring to is if y equals plus square root of 1 minus x squared, that's the top half of the circle. Minus square root of 1 minus x squared is the bottom half of the circle. that together make the full circle. The problem with the circle is it's not a function. It doesn't pass the vertical line test. So that's a big problem because it says find the particular solution y equals f of x. It says that y has to be a function. This is not. So the question is, how do we make this a function? How do we decide which portion of the circle we're on? Are we on the top part of the circle or the bottom part of the circle? That's the question. The top part or the bottom part? Well, we can figure it out because we know a point that's on the circle. Where is it? Right there. Okay? So since f of 4 is equal to -3, now you might already be able to figure it out, which is fine, but we're going to show the reader, hey, that you know what you're doing. We could plug in 4 -3 a second time. So -3 would have to equal plus or minus the square root of 2 times 4 cubed minus 59.5. So -3 would have to be plus or minus the square root of 2 times, let's see, that's going to be 4.5, 4.5. So that's -3 equals plus or minus square root of 9. The square root of 9 is 3. Well, which one is it to make the two sides the same? It's the -1. And we can conclude y has to be negative square root of 2 times x cubed minus 59.5. And that's the correct answer. Okay, including this explanation. You need to convince somebody that you understand why the answer's negative, not positive. Okay? And we're going to use the initial condition to do that. So we ended up using the initial condition twice here. We used it once to find C, and then once to figure out which portion of that circle, so to speak, we were on. All right. Okay, so let's try another one. Find the particular solution y equals f of x to this differential equation with initial condition y of 5 is equal to -4. All right, so first thing I'm going to do, I'm going to separate, multiply both sides by dx, divide by y. So I'm going to get dy over y equals 3 sine 4x dx. Notice I didn't take the 3 and move it over also. I think it just kind of gets in the way. I tend to keep constant multipliers on the right-hand side. I don't like to move them because, to be honest, I think they just get in the way over here. And, you know, if you think about what's going to happen, we're going to eventually solve the equation for y. So whatever I move over here, I'm going to have to end up moving back anyway later on. So I just keep it over here. Okay. All right, so now we're going to integrate this. On the left-hand side, the integral of dy over y, that's a rule. That's the natural log of the absolute value of y. On the right, the 3 can come out. I need to integrate sine 4x, so I need to use substitution for that. Let u be 4x. Its derivative is 4dx. I need a quarter for Beach Boys. So that's going to be 3/4 the integral of sine u du. So the natural log absolute value y. The integral of sine is minus cosine. And if you don't mind, instead of cosine u, I'm going to write cosine 4x and stick a plus c on it. Okay, now I need to solve this for y. I'm sorry, I don't need to solve for y yet. I need to find c. So y of 5 is equal to 4, a -4. That means the x is 5, the y is -4. The y, the outside, is -4. Inside is x. All right, let's plug it in and see what we get. So we get the natural log of -4 is equal to 3/4 or -3/4 cosine 20 plus c. Okay. The natural log of -4 is the natural log of 4. And then I'm going to add the 3/4 cosine 20 on both sides. And that's what c is. So c is this mess. All right. So now we have the natural log of the absolute value of y equals -3/4 cosine 4x plus the natural log of 4 plus 3/4 cosine 20. Okay, now I got to solve this for y. So I have to exponentiate on both sides. I get the absolute value of y equals e to the -3/4 cosine 4x plus ln 4 plus 3/4 cosine 20. Okay, now I'm back in the scenario that I was in earlier, where I have the absolute value of y is equal to all of this, but the absolute value of y isn't y, right? It's the absolute value of it. So I need to decide what to do with this absolute value. Now, if you're thinking to yourself, oh, wait, in the last video, we did a, okay? You're thinking in the right direction. That's the right idea. But we don't have a plus c anymore. We now have actual numbers here. So what we can do instead, we have numbers to work with. We know what the absolute value of y is equal to, right? Algebraically, it's this piecewise function. It's equal to itself if y is greater than or equal to 0. It's equal to -y if y is less than 0. All right, so that's good. We know that. So now the question is, which one is it? Well, again, we have this initial condition. Okay, what do we know about y? The number that's going in for y is -4. So we're on the bottom piece. So the absolute value of y in this equation is really equal to -y. So since 5 -4 is the initial condition, y is -4, so we're on the bottom piece. So that means the absolute value of y in this case is equal to -y. We know that for certain because of this initial condition. In the last video, we didn't have an initial condition to decide whether it was this one or this one. So we had to consider that it could have been both of them. So now the -y is equal to e to the -3/4 cosine 4x plus ln 4 plus 3/4 cosine 20. And now if you'll allow me, I need to take this negative and move it over there. So I got to multiply both sides by -1. Or what I'm going to do is just erase it. And I am going to put it over there in front. And that's the answer. That's the correct answer. Okay? The only other thing you could do with this is see where you have e to the ln 4. You can, instead of writing e to the ln 4, you can make that a 4. Because if you're exponentiating the natural log, it knocks out the natural log. So instead, you could have written y equals -4 e to the -3/4 cosine 4x plus 3/4 cosine 20. So you could write this also. That's also acceptable. All right. Okay, that's it for that one. So you can see what we're doing here. We're using this initial condition once to find c, and then we're using it again in some kind of tricky fashion to figure out how we could solve for y. All right, so now let's find the particular solution. This should not say r, y equals f of x. It should be r equals, let's say, r of t. To the differential equation, dr dt equals r minus 1 over t squared. Okay, so this is a little different. So now x and y aren't the variables anymore. It's r and t. That's okay. It's the same concept. I'm going to multiply both sides by dt. I'm going to divide both sides by r minus 1. And it's going to give me dr over r minus 1 equals dt over t squared. And now I'm going to integrate on both sides. On the left, I need to use substitution. I'm going to have to let u be r minus 1. du is equal to, well, 1 dr. So I don't need anything for Beach Boys. So this is going to be the integral of du over u over there. On the other side, t to the second comes up to the top, make it t to the negative 2. Add 1 to the power, divide by what you get on the right-hand side. On the left, it's the natural log again. And we're going to have t to the negative 1 over negative 1 plus c on the other side. So we'll move this down, replace the u, and now we have the natural log of r minus 1. Ooh, that's an r, sort of, equals negative 1 over t plus c. Okay, now we need to solve for c. So your initial condition r of 2 equals 3, just so everybody understands. That means t, the independent variable, is 2. The r value is 3. So I'm going to plug that in. The natural log of 3 minus 1 equals negative 1 over 2 plus c. So c is equal to the natural log of 2 plus 1/2. All right, so now we have the natural log of r minus 1 equals negative 1 over t plus the natural log of 2 plus 1/2. Okay, now we want to keep going. We need to exponentiate. Trying to solve for r. We're trying to get r alone. So now we have the absolute value of r minus 1 equals this e to the ln 2 that's in the exponent. I'm going to make it a 2 and stick it in front. Okay, so we're going to have 2 e to the negative 1 over t plus 1/2. All right, now, can I solve this for r? No, there's absolute value around it. Can I add 1 to the other side right now? No, I can't do that either. Okay, because that's also in the absolute value. So what am I going to do? I'm going to talk about my definition for the absolute value of r minus 1. All right, so the definition of the absolute value of r minus 1. Absolute value of r minus 1 is equal to itself, r minus 1, if r is greater than or equal to, not 0, 1. Right? So when I plug 1 in, it gives me 0. 0 is the point where the number changes from being positive to negative. And that's what I care about here, right? Because if the number inside the absolute value when I'm done is a positive, when I'm done with the calculation, if it's a positive, then the bars don't do anything. If that number after the calculation is a negative, then the bars do something. So I need to know where r minus 1 is equal to 0. It's equal to 0 because that's the changeover point when r is 1. If r is less than 1, then I get the opposite of r minus 1. All right. And now we know our initial condition. Since r of 2 is equal to 3, r of 2 is equal to 3. So r is 3. 3 minus 1 is 2, or 3 is greater than 1. So this is the definition I'm going to use. So in place of the absolute value of r minus 1, I'm just going to write r minus 1. Okay, I don't need to do anything. The bars don't do anything if I plug in the 0.23. And I'll rewrite everything else. And now I can solve this for r. The bars are gone. Add 1 on both sides. You get 2e to the negative 1 over t plus 1/2 plus 1. And that 1 is in line with the e. It's not up in the exponent. And this is the correct answer. Okay? So you can see what's happening here. We're using this initial condition to both find c and use it to continue and be able to solve for y or solve for r to get us out of some kind of predicament that we're in, whether it be a plus or minus or have an absolute value, something like that. Now, does that mean that you always need the initial condition to get yourself out of the predicament in part 2? No. Okay? So the two scenarios where it happens usually are with absolute value and with plus or minus. If you're just doing a problem where there's no plus or minus or there's no absolute value, 99 times out of 100, you won't have to use that initial condition again to figure out what your final answer is. You'll just be able to solve for it. All right? And that's how particular solutions work. As always, thanks for clicking.